Okay, everybody, welcome back. Today we are going to work with angle relationships in algebra. You see an angle on the board. Our goal today is to focus on a variety of different angle relationships and discuss how those relationships will yield equations to help us solve for unknowns and to help us solve problems. So you don't have to watch the video. This is a series within one video. You can check out the timestamps below, and those will tell you what type of relationship we're working with and let you fast forward or zoom so you can use this video for the best purpose possible. Okay, thanks for watching. Enjoy. Okay, so let's discuss adjacent angles. Adjacent angles are a pair of angles that are next to each other. So we're going to leave that tagline right below. Now, next to is, a way we could say nearby, but there is a key for adjacent angles. That a key is that the adjacent angles must share a vertex. Notice these two angles do. They share vertex B. And they must share a common side or a common ray. In this case, both angles have ray BD. So our two adjacent angles here are angle ABD and angle DBC. What does that mean for equations, building them, solving them? Well, the adjacent angles themselves are following a relationship and pattern that we're going to use to solve a couple of different equations here, in that I know that when I take a look at this image, ABD, the angle, is one part. DBC, the angle, is another part. Those two parts I've marked in green, which are not necessarily congruent, so let's just make that a double symbol. Their sum, their degree measure, must amount to the whole, the entire piece, which is ABC. So we're going to build an equation just as I said it. The part ABD and the part DBC must amount to the whole. We're going to use some equation symbols to kind of fit our sentence there. And we're going to use a little m to represent the measure of in degrees of angle ABD plus the measure of angle DBC must equal the whole, which was angle A, B, C, their measure. Now remember, when we're talking about equal signs, we have to actually have values. So this is an angle measure denoted by that M. This is an angle measure, and then the one I barely could fit in here, measure of ABC, the whole, represents the total degree measure of both combined. A more simplistic way of thinking about this would just be able to say part versus and part, not versus, part plus part equals whole. Thought process that will come into play with a future angle relationship as well. So if you're given a pair of adjacent angles, you might not necessarily be given a specific degree measure. You might not be given degree measures for the parts. But what you can count on to build this equation is that the sum of the parts must equal the whole, the entire thing. All right, thanks for watching. Look for the other angles in the description below. Okay, everybody, welcome back. The next angle relationship we are going to discuss is a linear pair. Linear pairs fit the criteria of two angles that we've discussed throughout this unit so far. They are an adjacent pair of angles. They lie together, sharing a vertex, as you see here, on a line. And they are supplementary. The reason we know they're supplementary is, again, because they lie on this straight line. Straight angles, and all the angles on that straight angle will always sum to 180 degrees. So like adjacent angles, this is a situation where when we build our equation, we want to work on an equation that looks like this. Part plus part equals whole. Unlike adjacent angles, the whole is not a mystery. I don't need to worry about having an expression for the whole. I don't need to worry about being given a degree measure. In the case where the line is straight here for a linear pair, the whole is going to equal 180 degrees. So using this example as a guide, whenever you're faced with a linear pair and you're looking to solve for x or find an unknown and then find a missing angle, your goal is to create an equation where we set the two parts and their sum equal to the whole, which is going to be 180 degrees. So in this case, the measure of angle 1 plus the measure of angle 2 is going to equal 180 degrees. That's the equation that we associate with linear pairs. Okay, if you're looking for more angles, look in the description below to see the timestamps. Thank you. All right, everybody, we're back with another angle relationship. Vertical angles. Vertical angles are angles that are created when two lines intersect, just like the ones you see on the board. When two lines intersect, the angles across from each other, the opposite angles, are congruent. They are equal in measure. So angles 1 and 3, because they are across from each other when the lines intersect, would be congruent. They'd be equal in measure. Same can be said about angles 2 and 4. We'll differentiate with the green and the double markings. They are also equal to each other. So equations. What equations stem from a pair of vertical angles? Well, they're pretty straightforward. 1 and 3, they're the same. which means that they're equal. So measure of angle 1 is equal to the measure of angle 3. What about 2 and 4? Well, they're the same. So the measure of angle 2 is equal to the measure of angle 4. So given a pair of lines that intersect, it's easy to find the angles that are the same, which would help us set up equations for those. If you notice with intersecting lines, so we're straying off course a little bit here, you'll notice that we also have a host of linear pairs from our previous video that pop up. 1 and 2 are linear pairs, 2 and 3, 3 and 4, etc., 1 and 4. All of those pairs add up to 180. So you should expect questions where you are given an expression for a couple of these angles. You have to set up the correct equation, whether they're equal or whether they sum to 180, and then use the unknown that you find to plug in and find every degree measure in this picture, either by using the 180-degree relationship or using our new relationship, vertical angles, where the opposite angles have to be equal to each other. Okay, for any remaining angles, check below for the timestamps or go backwards to the other angles in the timestamps. Thanks for watching. All right, everybody, another angle relationship for you here. We are going to discuss what an angle bisector means for angle relationships and equations. On the board right now, you see a pair of adjacent angles. You see ABD, DBC. This ray here, BD, I'm going to call an angle bisector, right? So because ray BD is an angle bisector, it is going to cut angle ABC in two. Angle bisectors cut an angle in half into equal parts. So if I'm given the information that a ray or a line segment is a bisector for an angle, what that tells me is simply put that the two parts are congruent to each other. Or another way of saying it would be to say that a part would be half of the whole because it is bisected. So naturally, two equations come or stem from this situation. If I'm told that BD was a bisector for the angle on the board ABC, that means that the part ABD must equal the other part because they are cut in two, they're cut in half. So one equation possibility would be to say that part equals part. Okay, in this instance, specific instance, that would tell us that I could set up an equation given the right information that the measure of angle ABD is equal to the measure of angle DBC. Now, the other equation situation that spurs from this from an angle bisector would be this idea that one of the parts is equal to half the whole, or twice one of the parts would equal the whole. So I did this in a previous video. I had them marked red. These are actually congruent. I'm going to elaborate on what the whole is with that green marking there. ABC would be the whole. So an equation that stems from this angle bisector situation would be to say that twice the part equals the whole. So in our case on the board, it would be fair to say, if I had an expression for angle ABD, that twice the measure of angle ABD would equal the measure of the whole ABC. You could, of course, do the same thing for angle DBC as a part, since both parts are equal to each other. You have to be very careful getting a question that involves an angle bisector, not to make the assumption for either case. I think most people jump to this conclusion and just want to set everything equal to each other. Take a look at your equation after you're done. Take a look at the information given and make sure when you read your equation that looks like this, that when you look at the picture, it makes sense, right? If you're given some information about the whole and a part, it shouldn't make sense for you to set them equal to each other when the whole is obviously way bigger, all right? So when we're working with angle bisectors, our goal is to set up one of two types of equations. We either want to set the parts equal to each other if that's what we're given, or we want to double one of the parts to set it equal to the whole.